light it? No. I told you. It's getting fancy here.
Well, on behalf of the physics department, I'd like to welcome you to our, I guess this is our 9th Faraday lecture, and next year is going to be our 10th anniversary. I think we'll try and do a little something extra special for it, if we survive this one. With a little bit of luck, we'll make it. I'm Mark Croft, and this is Dave Maiulo, who really makes everything happen here.
Yeah, right here we have a crew of students that we have had for the past few years, and really they're the ones who really make things run. They're the ones who come. Big round of applause for them.
Now we're going to follow a format that's a little bit like our introductory physics courses, and that will be the subject matter. The idea here is that we do this lecture out of love. We do it out of love of physics, out of love of science, out of love of learning, and there's nothing feels so good as to pass along something you love to somebody else, and that's why we do this physics. And we found that when we do our lecture demonstrations for the students, that they tend to like the demonstrations that embarrass the professor, better yet, endanger the professor, and the absolute payoff is if it really injures the professor. So we sort of play up that angle here. I should emphasize that we're never really at any time in danger here. However, some of the stunts that we do here are circus tricks and should not ever be attempted by anybody else. A few selected ones are just circus tricks. I'll enumerate those carefully. Okay, when you start an introductory physics course, the first thing you learn about is that objects at rest tend to stay at rest, especially if it's myself watching football or something on a couch. And that the more massive the object, the more it tends to stay at rest. And here is our first demonstration. I have a series of objects on this table. Of course, this is my wife's finest china. And they are at rest. And when I pull the tablecloth out from underneath, hopefully they'll stay at rest. Oh, yes, yes. I'm fully insured, but not my glasses. Okay, so let's see. So actually, there's more to this. There's actually, you have to worry about coefficients of friction and how fast you accelerate things. But this sometimes works. So, objects at rest tend to stay at rest, and the more massive they are, the more they tend to stay at rest. And here I have 3 objects. I have a nice little sponge. It doesn't have much mass. It moves around very freely, and if I put a force on it, or a push, it changes its motion, and, oops, sorry about that. The first row actually is a little dangerous here sometimes. And now this object is somewhat less massive, and put the same push on this guy, well, he goes a little bit, and get a little closer to you than I wanted there. But you're safe on this one, because this is a piece of lead, and I can hit it quite hard, and it goes back to rest. As a matter of fact, it's so massive, I can put it on my hand, and beat on my hand, and it doesn't hurt at all. Okay, so those are objects at rest that tend to stay at rest. There's a second part to that, and that's objects in motion tend to stay in motion. Now the ancients, when they developed some of their rules for looking at these things, had a real problem with friction, because if you put an object down on the floor and you want to make it move, you have to push on it. When you stop pushing on it, it stops moving. And so they have an object always liking to be at rest and trying to get back at rest, sort of like me again, on the couch. But in fact, we now have the technology to turn this into a hovercraft and get rid of friction. And then you'll see that an object once set in motion, if not acted upon by some other push, will move forever in a straight line at a constant speed. Constant direction and constant speed. Okay, I think we better get that off the floor now. If Aristotle would have had that, we would have been thousands of years ahead of time. Okay, so that's objects in motion tend to stay in motion. Now,
One more.
yes. Dave is now going to do one where an object in motion is going to tend to stay in motion, and it's going to be a pencil. Now, Dave will let you
Yeah, in
explain
this
this.
case, what's this object right here? Right. And there's a little tube here, and before you guys got here, we took a pencil, we shoved it all the way down this tube. And you can see there's a piece of wood over here. What we're going to do is we're going to accelerate that pencil. We're going to see what happens to this piece of wood once the pencil leaves this tube. We're going to accelerate it also with this fire extinguisher. All right, now, I'm supposed to be a professional here, so I'm allowed to play with fire extinguishers. So please don't touch these things, okay? Please. Otherwise, unless there's a fire, because we actually modify these and do certain things, so that don't touch them outside of this place. But myself, I get to do this kind of thing. They pay me to do it. Can you believe it? On 3. 1, 2, 3. Happened pretty quick, didn't it? So our pencil was in motion, and it went right through that piece of wood. Pretty hard to believe. And actually, think about this. They go farther if they're not sharp. Why? I'll let you think about that. You want that, right? Thank you.
Okay, the next thing is we do the next of Newton's laws that we tend to do is the force reaction force law, which is the you push me, I'll push you just as hard, but no harder rule. And so you have to have a two-component system to do that. And here's a balloon, and there's air inside the balloon, so this is a two-part system. When I let go of the balloon, you all know what's going to happen. The balloon's going to go shooting off this way, and it's going to be shoved in that direction because it shoves the air in this direction. And so this guy goes flying around the room. Well, that's one you can do at home. But the students tend to think that's not so exciting. So they like me to take the place of the balloon. And to do that, I have here a 50-pound fire extinguisher, and I'm going to fire it